Thank you, Rick. Appreciate it. All right. Thank you, everybody. Um, yeah, Shelley is a great act to follow. I hope I can do as good as she did. But okay, so if you guys don't know who I am, some of you may not. I am the host of Globebusters, and we do a show every Sunday at noon Pacific, 3 p.m. Eastern. And myself, Iru Jaron Campanella from Jaronism, and Taboo Conspiracy Ben, all do this. And our approach, what we try to do is kind of bring a common sense type of approach to this. Ooh, I'll try not to walk around too much so we don't mess around with the audio. But we try and bring a common sense approach to this, and obviously there's a lot of math, and when people go into mathematics, a lot of people tend to glaze over. So I try to present things in simple concepts. Okay, so what we're going to do today is we're going to talk about a few different things. Yee. Wow, where is that coming from? Okay, we're going to talk about a few different things that are kind of common sense things that we like to talk about. I'm going to talk about star intensity and the moon, and whether or not we should be able to see them. We're going to talk a little bit about the ISS, and we're going to talk about some brightness issues that we have found with the moon. So I'm going to go ahead and get started, and I've titled this, "Oh My Stars, It's Impossible." And it is an expose on the inverse relationship of size and distance and the inverse square relationship of light intensity and distance. Okay? Oops, wrong button. All right. So there's a few things that we want to consider when we're thinking about stars and planets. We all look up and we see the stars and we see the planets, and they're all pretty much the same size, twinkling little lights, and they tell us that there are, millions, thousands, hundreds, thousands, millions, billions of light years away. And, that has always been a really hard pill for me to swallow. And, astronomers, fortunately, because they can't actually measure these things, even though they would try and convince you that they cannot. So what they do is they make a whole lot of assumptions and a whole lot of guesses about, the information that they're presenting to you. So fortunately, they get to make up the math, they get to make up the numbers, and then their math pretty much checks out on a lot of things. But again, like I said, we want to bring kind of a common sense angle to this. So some things to think about when considering stars and planets is the inverse relationship of distance and angular size is a measurable and mathematical fact, okay? And when distance is doubled, this is an example, when distance is doubled to an object, if you're looking at it, and say I have an object that's 6 foot in front of me, and I double my distance from maybe 10 feet to 20 feet away, the angular size is going to be cut in half. In other words, it's going to appear to shrink to half of its size. Conversely, when distance is halved, the size is double. So if I move closer to something, it's going to grow bigger and bigger, bigger in my field of view. Okay, common sense stuff. We all know that. Okay, so the inverse square relationship of distance and light light intensity, is also measurable and a mathematical fact. Again, like I said, we can measure it, we can do calculations on it, it's there, it's a reality. All right, so the inverse square law, let me tell you what it is, a little bit about it. And the concept of it is that when you have a point source light, or actually almost any light source for that matter, when it's shining out, like these spotlights, for example, you have a very high intensity, at a very close distance. But as you get further and further and further away from it, it actually starts decreasing in intensity. So the Wikipedia definition is the inverse square law in physics is any physical law stating that a specified physical quantity or intensity is inversely proportional to the square of the distance from the source of that physical quantity. The fundamental cause for this can be understood as geometric dilution corresponding to point source radiation in three-dimensional space. Now that's just kind of a technical description, but to give you a better idea, and you can kind of read the narrative there, but you know, when we look at this, you have a point source, and then say you have a meter away and you have 1 meter, that is giving you a certain intensity at 1 meter away. But then when you double that distance, you can see that now you have to square that, so now you have that same light intensity that has to cover 4 times that area. If you triple that distance, then it has to cover 9 times that area, and so on and so forth. 4 times 16, 5, 25, etc. Okay, so that's basically why, you know, light cannot remain infinitely bright, and this also applies to radio waves, radio transmitter waves. You know, NASA would love you to believe that they can have a 20-watt transmitter and it can transmit billions and billions and billions of miles, you know, on the spacecraft, but somehow we have to have 50,000 watts plus just to have it listen to our AM radio station around the city, right? That doesn't make a lot of sense to a lot of people. So, all right, so let's move forward. And so let's talk about our sun. And our sun, obviously, this is something that, you know, we can look up and, you know, we see this ball in the sky and it has an angular resolution of about 0.52 degrees, or just a half a degree, not very big, about the size of a frisbee in our sky, you know, if you're playing frisbee. Not too big, and this is something that we can all observe. But what we can't necessarily observe, nor can we triangulate, is the actual distance to it. So we have to rely on what NASA tells us, all right? So let's go ahead and look at some of these facts. The first thing is that they say the distance to the sun is 92,960,000 miles away. Now that is a big number. None of us can even remotely comprehend that, but you know, that's kind of the NASA strategy to, you know, baffle them with bullshit if you can't dazzle them with brilliance, right? So they tell us it's that far away, and at that distance, if you're traveling at the speed of light, it takes just slightly over 8 minutes for that light from the sun to get here, all right? All right, we can accept that. Next thing up, the diameter of the sun is an astounding 864,340 miles across. Again, another incomprehensible number, but you know, that's what they tell us it is, so that's what we're going to operate from. And we're going to actually kind of look at that in, you know, in comparison to the rest of the solar system. So the brightness of the sun, as measured here on Earth, and this again is from Wikipedia, is measured in lux. And a lux measurement is a measurement that means lumens per square meter. And I'm going to give you a demonstration of what, you know, what 6,500 lumens looks like here in just a minute, just so you can kind of put this in context. But in bright daylight, everybody's experienced bright daylight, we're talking about 98,000 lux measured, you know, here on Earth. So they also tell us that the sun is just an average-sized star. So it's not the biggest star out there, it's not the smallest star out there, it's an average-sized star. Okay, fair enough. So with that information, we're going to do a little bit of simple math, and this is very, very simple math. And I'm actually going to need to put my glasses on so I can read this. But if we are talking about a sun that is 93 million miles, okay, and these again are NASA's figures. That puts it about 8 light minutes out, and we know that we can measure the sun in our sky at about a half a degree, all right? So again, according to the inverse relationship of size and distance, we can now bring that distance out. If we double that distance to 186,000 miles, which is 1 light second, right? 186,282 miles per second is the speed of light. I'm sorry, 186 million, I missed that one. 186 million miles, which is 16 light minutes. We cut that angular size in half to 0.26 degrees, all right? So now we're starting to reduce the size of the sun. If we double that again to 372 million miles, 32 light minutes, that's 0.13 degrees angular size, 1/4 what we see it in the sky. And we double it again to 744 million miles, 1 light hour, 0.065 degrees angular size. And then we get out, I highlighted this next one because we're going to be doing something, a little bit of a thought experiment with Saturn. So the Saturn is average distance of about 893 million miles, or 1.33 light hours away from the sun, okay? It has an angular size of 0.45 degrees in the sky, and the sun has the angular size of about 0.45 at Saturn. Okay, and that's the distance to Saturn, all right? So if we continue on, we go 1,488,000,000 miles, 2 light hours. Now the sun has an angular size of 0.0325 degrees. It's getting smaller and smaller and smaller. You know, pretty soon it's going to be imperceptible. And then the next thing that I highlighted here is what is called our visual acuity limit, and it's also our angular resolution limit. And what that means is that the very smallest objects that we can see actually have this 0.02 degree size, little bitty, teeny tiny, right? If it goes any smaller than that, we can't see it. Now, before anybody starts talking about, well, yeah, but light's different, yes it is, and we'll get to that. So I just wanted to highlight that the 0.02 degrees is actually our visual acuity limit. So if we continue on, going out to 2,976,000,000 miles, that's 4 light hours. Now the sun is looking at 0.1625 degrees of angular size. It's getting smaller and smaller and smaller. And mind you, we're only 4 light hours out, right? It's almost gone. So now the next thing that I've highlighted is Pluto. Pluto's average distance to the sun is 3,670,000,000 miles. Okay, that's way out there. And of course, we cannot see Pluto with the naked eye because we have gone a couple steps below our angular size limit. So if we continue on and we go to 5,952,000,000 miles out, 8 light hours out, 0.008125 degrees. In other words, we're starting to get, you know, pretty close to the size of a star, right? Getting smaller and smaller and smaller. And finally, we're going to take it to 16 light hours, which is a mere 2/3 of a light day, okay? And that's 11,904,000,000 miles. And so essentially, what my point is here is that in less than 1 light day, only 16 light hours, the sun's angular size is 5 times smaller than we can actually even see. All right? Now, that's if it was not lit, okay? Now, when it's lit, it's a little bit different story. So let's move on. So, as I said, the objection is going to, well, what about the brightness? You know, you can definitely see things bright. You can't necessarily see the wick of a candle, you know, like Wendell and Shelley were showing at 1.5 or 1.6 miles, but you can see the light. Okay, fair enough. But the light also, you have to take into consideration that it is stepping down, it's not halving every time, it's going down in a square relationship. So it's going down in intensity even more rapidly than the angular size is. So we're going to look at that, and there's a really simple formula for solar intensity, and that's I is intensity is 1 over the distance squared, okay? Again, the inverse square law. So I made up a little chart here, and this is kind of cool because this gives you an idea of what the sun's intensity is on different planets, okay? So Mercury, obviously, since it would be so much closer than Earth, you would have the solar intensity would be about 6.68 times brighter, okay? Venus, the next closest planet to the sun, would be nearly twice as bright. The sun would be 1.913, and Earth being the benchmark, because this is the one thing we can actually measure and not have to take NASA's word for it. So we're going to call that relative solar intensity of 1. Mars, when you get out to Mars, it's only about 43% of the brightness of the sun here. And I find that interesting because when you look at NASA's pictures of Mars, you know, they show it, you know, lit up almost as brightly as Earth, right? Which is crazy because the inverse square law dictates that it has to be less than half as bright, but they don't really portray it that way, do they? So you get out to Jupiter, it's down to 0.369, so down to 36%. And then when you get to Saturn, it's at 0.11%, or basically it's 100 times dimmer on Saturn than it is here on Earth. Okay, so what's my point with this? Okay, well, if the light reaching Saturn, and you really need to think about this for a second, if the light reaching Saturn is 100 times dimmer than what we experience here on Earth, right? What exactly does that mean? Now, first of all, when we talk about light source here on Earth, you know, when they give us that 98,000 lux figure, that is not from direct sunlight. We also have what they're telling us, that the light is diffused through the atmosphere, because obviously you can go and you can stand in the shade somewhere, be completely blocked by the sun, but in broad daylight it's still very, very, very bright outside, right? So a lot of that brightness of that 98,000 lux is from the dispersal of light. Now, there are different theories on how that actually happens, but you know, according to the mainstream explanation, it is basically being diffused throughout our atmosphere. And then that gives us our, you know, that combined with the direct sunlight gives us our 98,000 lux. All right, so the point here is, since Saturn is 10 times further away from the sun than the Earth, it is receiving light at a mere 1/100th the intensity of what it is on Earth from a sun that is only 0.05 degrees angular size. Now remember, 0.05 means the sun is 10 times smaller on Saturn, and it's 100 times less bright on Saturn. So we have this other thing that's called albedo. An albedo figure is something that is the reflectivity of a planet. Like, you know, Earth has a certain albedo because it has the oceans and it's reflecting light. The moon has this albedo figure because it's reflecting so much light, etc. So all these things taken into consideration, if you were standing on the surface of Saturn and you're barely seeing the sun, you know, because it's, you know, 10 times smaller than it is here, it's 100 times dimmer than it is here, and yet somehow we are able to see Saturn in our sky shining very brightly 1 billion miles away. All right? Now, NASA has very neatly done the math for this so that, yeah, okay, this can actually work out, but they don't really address the idea of, you know, a point source light versus a, you know, a total light figure with atmosphere and dispersion and stuff like that. So that's one of the first things that you need to think about. It's like, does that really make a lot of sense to have something that's dim, and here we are looking at it all this distance away, and you know, it's really, really bright in the sky. In fact, you know, the way that Saturn looks in our sky isn't a whole lot smaller than what the sun would look like at Saturn. In fact, we're actually going to take a look at that here. Back? Yeah, we're back. That's crazy. God has spoke. All right, so we're going to look at a little chart here in a second that shows how the sun appears on other planets. And this chart was put together by a place called My Science Academy. It is a mainstream science site, all right? And they're going to show us the pictures of actually what it looks like. So the one thing down here at the bottom, it says, to avoid any confusion when you're looking at the image, the little spaceship seen in each frame is irrelevant to the overall point. The original designer put it there to help establish how much light the sun generates on each planet. Each comparison was based on the approximate apparent visual magnitude of the sun for each planet, meaning that the little spaceship is going to show you how bright it is, you know, when it looks there. So let's look at that. So here it is. So Mercury, we've got this big old sun in the sky. It's huge, and you can see the little spaceship down here is lit very, very brightly. Venus, it's of course quite a bit smaller, and it's not lit nearly as brightly. Then we get to Earth. You can see what's happening there. Now Mars, interestingly enough, they're showing that that little spaceship is being fairly dark. And remember, Mars has got a whole lot less sunlight than we do, so it's even amazing that they do this. But, you know, the sun actually shines pretty brightly on Devon Island, which is really where Mars is, right? So, okay, so then we look at Jupiter, and then there's Saturn. Remember, 1/100th the intensity, 10 times smaller, and there it is. And the little spaceship is almost in complete darkness, right? So these are the things, and then by the way, by the time you get out to Pluto, and they don't even show Pluto on here, but the article that I actually pulled this from that was by My Science Academy says, you know, how does the sun look in on other planets? And it just says straight up, well, by the time you get to Pluto, it's just another star, right? So, and that isn't even a light day away, guys. That's crazy. I mean, they want us to, you know, they give us demonstrations like this, and they have to, you know, based on, you know, their claimed distances and everything. But if the sun in eight light hours, or 2/3 of a light day, is too small to see angular-wise, and brightness is orders of magnitude dimmer, right? How in the world are we seeing stars at, you know, well, the closest star is Proxima Centauri, right? And that's like 4.4 light years away, something like that. I mean, there's a huge difference between 8 light hours and 4 light years, right? And remember, our sun is an average-sized star. And yet, they're telling us that we're seeing stars dozens, hundreds, thousands, tens of thousands, hundreds of thousands, millions, and billions of light years away. And it's just preposterous. And the only way that they are able to make their math work is they will sit there and tell us things like, well, Polaris, for example, is supposedly, well, it was 450 light years away. Then, of course, they had to revise it to, I think, 323. So they only had a mere, you know, like 130 light year, just a small error, a mere 130 light year discrepancy in that. So they revised it. So they tell us now that Polaris is about 323 light years away. But its brightness is about 4,000 times brighter than our sun. And they do this, they just make this stuff up so that they can make the math work as we come here. Because remember, they have no way to measure this. It's all a mathematical construct to them. You know, there's nobody that has ever been there that has actually measured the size of Polaris, and nobody has ever been there to measure the brightness of Polaris. But, you know, they will have you believe that somehow, without knowing either one of those things, that they can tell you everything about it, you know, which is preposterous. They simply cannot. All right? So just some things to think about, you know, about when you look up at the stars in the sky and what they tell us, how far they actually are. I mean, the notion is ridiculous, frankly. All right, so the next thing I want to talk about, and I talk about this on Globebusters. I've actually talked about it a few times because I find it kind of an amazing thing that people really believe this, but so one of the things that we talk about is the International Space Station. Now, our Glober opponents would love to tell us, and they would love to validate NASA by saying things like, I know the ISS is real. I've seen it with my own eyes. It's absolutely there. You can't deny it. We can take pictures of it. It's there. You guys are just idiots, right? All right, okay. I agree. We can see it. There is a website that you can actually look up, and it will tell you the times that NASA passes over, the ISS station passes over, and you can look it and you can observe it, and people photograph it. Everything. Yeah. Okay. It's there. Great. So, but I want you to think about a few things. So first, let's get some facts about the ISS. What do they say about the ISS? Well, these are kind of boring statistics, but they say the pressurized module length is 167.3 feet, or 73 meters. The truss length is 357.5 feet. The solar array length, 239.4 feet. Mass, blah, 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 etc. And of course, mind you, guys, this is the most expensive engineering project and the most incredible accomplishment that mankind has ever achieved, and there is not one single photograph or video of this station being constructed. Not one. Now, that's crazy, all right? That, first of all, should really make people, take notice. And of course, the ballers will come back and they'll say, oh, no, we've got these. And they'll literally show you animations of them putting these modules together, in high speed. And it's like, yeah, there it is. There's our documentation. It's like, all right, whatever, if you want to believe that. So all right, so let's go to some ISS facts continued. So they tell us that the ISS travels around the Earth at about 17,500 miles an hour, and that varies plus or minus 300 or 400 miles an hour, which breaks down to about 5 miles per second. Now think about that speed for a second, guys. 5 miles per second is one of those numbers that, again, is absolutely incomprehensible, all right? So they say that the ISS is the size roughly equivalent to the size of a football field or a 747, and that's true overall dimensions, but we're going to look at the angular size of it here in a bit, and I'll get to that in a second. But so the largest, the orbital height of the ISS is 254 miles up. Well, first of all, you cannot see an object 254 miles up because it has a calculated angular size of about 50 arc seconds. Remember, our visual acuity limit is 60 arc seconds or 1 arc minute. Okay, so you can't see it. So they're really relying heavily on the fact that because it's supposedly reflecting the sunlight down to you, that's what makes it so that you're able to see it. All right. So the largest area occupied on the ISS are, of course, the solar arrays. They're mammoth. They're huge. When you see it, do its little transits, it looks like a little TIE fighter, kind of goofy looking. Really a ridiculous engineering design, but, whatever. So, and solar arrays, which are the largest area occupied, are designed to collect light, not reflect it, all right? There is no external lighting on the ISS unless the astronauts are going out there for a swim, spacewalk. Then they will take some light out there, but other than that, it's not lit because, they don't want to burn up their power reserves, all right? So, as I said, the calculated angular size of the ISS is about 50 arc seconds when it is directly above you, at that 254 mile, which, like I said, is below your visual acuity limit. All right, and also, that's being generous to them, and that would be, assuming you could see it, that would be if it was a solid object, right? And it's not. It's very strung out, and you've got the fuselage, and you've got, all these different pieces parts, but it's not a solid object, so really giving it 50 arc seconds is generous in a lot of ways. All right? So, now, what I want you to do, now that I've given you all the facts about the ISS, is I want you to put your common sense hats on, right? You don't have to do any math here, just put some common sense hats on. There is a website at this web address, https://spotthestation.nasa.gov. What this does, guys, is this will tell you you're able to enter in your location, your zip code, whatever, and it will tell you when the ISS is going over you, and where it's going to rise, how long it's going to stay in your visual sight, and when and where it's going to set. It tells you everything you would need to know to be able to spot this ISS light in the sky. All right? So, the typical transit times when you look it up are anywhere from 2 minutes, and this depends on what day and where you are in the USA. And the typical transit times are anywhere from 2 minutes all the way to 8 minutes. All right, so that's quite a viewing time, especially when you are considering that at 5 miles per second, right? Remember that unimaginable speed? That translates to you are able to see it from anywhere from 600 miles to 2,400 miles, and of course adding on that extra 250 miles up, we're looking at about a 2,600 mile viewing area for something that is the size of a 747, maybe a little bit bigger, right? This is getting more and more ridiculous all the time. So now science is really, really counting on you being able to see it because of that reflected light off of it, all right? So, and they say, of course, that the reason that you're able to see it is because when you have the ISS going over the Earth, usually it's typically just before sunset and right before sunrise, right after sunset and right before sunrise, right, where the sun theoretically is just below the horizon of the ball, and it has this angle that it can shoot up, right? Well, that's the theory, but interestingly enough, there are certain websites that claim you can see it at all hours of the night, which is frankly impossible, but I haven't, checked the veracity of that. So let's take a look at this, all right? So what I'm going to show you here, and this was amateur footage. I did not shoot this, just so, nobody can claim me of shilling it. But this was taken right off YouTube, and this is somebody that just did, they put their camera on it and they recorded the ISS going over. So we're going to watch this for a minute, and I want you guys to really look at this and think about what you're seeing here. So let's watch this. Oopsie, that didn't work. Why are we not playing here? Ah. I don't know, so we got any PowerPoint experts here? Tell me why this isn't playing. I can actually play it. I can play it a different way. Let me just do it that way. How do I do that?
Get out of the slideshow. Stop the show. Now play it from that window.
All right, we'll just do it from here. All right. Okay, let's try it this way. Sorry, I'm not a pro on PowerPoint. So let's do it this way. Okay. So how many of you have actually witnessed an ISS transit over the top of you? Show of hands. All right, well, quite a few of you. And like I said, if you haven't, you can see Spot the Station. You can go and do this for yourself. You guys, would you say that this is an accurate representation of what you see? All right, fair enough. So I didn't make it up. Like I said, this is amateur. I just pulled it off of YouTube. So I hope that while you were watching that, you were kind of thinking about this, right? About what you're seeing. I mean, not only about the fact that we're looking at an object that is allegedly going, 10 times the speed of a bullet, right? 5 miles a second, ridiculous. But the other thing that struck me about this is, how is it that we are able to see it the entire time across the sky? It never seems to change angular size. It doesn't ever seem to change brightness. So what I did then is, so I want to ask you a question. How many of you guys have ever just played with a mirror reflecting sunlight around, right? Okay, so you know that if you're trying to, use the sun, if I had a mirror up here and I was, gonna try and, hit one of you, it's kind of a tedious thing to try and do. So to kind of accentuate that point, what I want to do is I want to play this, and this is kind of neat. I found this experiment in the UK about people lined up, the width of at least a football field or the length of a 747, and they're all playing with mirrors. So check this out. This is kind of cool. Oops. All right, so you should really, that should really make an impact on you when you think about that. So what all these people are doing is they're trying to reflect sunlight, playing with mirrors, reflective surfaces, and as you saw, we are only seeing occasional flashes here and there. In other words, what I'm saying, guys, is it takes a very specific angle. The geometry demands it. It takes a very specific angle for something to flash light directly at you. So you need to ask yourself a question here. If the ISS is only 3% above the 7,918 mile diameter of the Earth, how is the sun able to reach the bottom of the ISS with the angle required to reflect that light down to your eye? Oops, getting a little feedback. And also, do that continuously. So how does the ISS manage to keep that reflected light coming perfectly into your eye while traveling at 5 miles per second for a distance of 2,600 miles? And again, it doesn't ever seem to change angular size or brightness. It's just the whole thing. The next thing, of course, is at the same time you're watching the ISS, how does it also keep that reflected light coming into the eye of an observer continuously across your city or state? Okay? Yeah, that's it. It's refraction and gravity. That's got to be it. So you guys you should be seeing a problem here, right? There's no way humanly possible that this can happen. So those people that say, I can see the ISS across, they obviously have not thought things like this through. This unequivocally proves that it is fraud, and it also means, the other question that I didn't put in here that you should ask, is that if we are able to see this from our vantage point for 2,600 miles, literally across the entire United States of America, why do they have to have certain times of day for different regions to be able to see it? My God, if I can see it for 2,600 miles from wherever I am, you would think that anybody else would be able to see it from there as well, wouldn't they? But they can't, right? That's another huge problem, right? Again, critical thinking, guys. You got to ask these questions, all right? So you got to ask NASA, how? How, NASA? How? The answer, of course, you guessed it, it is impossible. It can't happen. Yeah. All right, so last thing I'm going to do, and I know I've run out of time, but I want to do one other thing and show you something really interesting about going back to the inverse square law. And let's go back to the moon, all right? When I was talking about the inverse square law, and let's take a look at it in terms of the moon. So you remember that pesky inverse square law of light thing we covered at the beginning? Well, let's have another go at it using the moon's light that we see here on Earth, okay? Now, Wikipedia and other mainstream sources seem to have a pretty wide variance on what the intensity of moonlight is. And by that, I mean that some entries, Wikipedia itself says that the moonlight is 0.1 lux, okay? And that's fairly dim, but it's enough that you can read by it, okay? And all the way up to 1 lux. And I think my partner, Taboo Conspiracy, used a 1 lux figure. Like it said, it depends on what source you want to go to, but it really doesn't matter with what I'm going to show you here. So Wikipedia and other mainstream sources seem to have a pretty wide variance on what the intensity of moonlight is, but let's give science the benefit of the doubt and use the lowest figure, which is obtained from Wikipedia. So here's a little bit of math here, but that's okay because we're going to use a calculator. And I do have the calculator in here. It's an inverse square law calculator. But I'll show you what the formula is. I'm not actually going to do the calculations. I already put the numbers in, and you guys absolutely can do this yourself, because when I saw Ben do this and actually Jaron do this, you know, I looked at that and it's like, that cannot be right. That cannot possibly right. That number is so wrong that it just can't be right. All right, so here is the moon problem. According to Wikipedia, the moonlight intensity for a full moon is 0.1 lux. A lux is the psi unit of illuminance, equal to 1 lumen per square meter. The brightness of 1 candle, right, 1 candle pair, remember Wendell and Shelley, they're out there doing that 1 candle, is equal to 12.57 lumens at 1 square foot. So in other words, a square foot box around that candle gives you 12.57 lumens. So, next factoid, average distance to the moon is 384,402 kilometers, or 238,856 miles. The formula to determine the luminosity using the inverse square law, E2 is distance 1 divided by distance 2 squared times E1, and I'll show you this in a second, all values in meters, where D1 is the original distance measurement, the surface of the Earth, i.e. the 0.1 lux. All right. D2 is the new measurement distance, which would be the surface of the moon, and that's our D2 figure. And E1 is the original measurement, all in lux, the original measurement here, of course, being here on Earth of that. And so now we have our D1 number, and we have to convert this to meters because everything is done in meters. So 384 kilometers is 402 million meters, all right? There's our figures. And before I show you what this number is, it's crazy. I'm gonna show you something. I have this little flashlight here. And this little flashlight, I call it the portable sun, is a 6,500 lumen flashlight. So it's pretty bright, but so I want to show you what that is before we actually go to this next number. So if I turn it on here, oops. So if I do that, you guys look at that, there you're looking at a 6,500 lumen flashlight. Okay? Getting the idea here? It's pretty bright. And that's, by the way, would be measured at 1 meter. All right, so it's considerably dimmer when you get out there. All right, guys, here's the time for the big reveal. This is insane. So if we take that little 0.1 lux or lumen, okay, and we reverse calculate it using the inverse square law, the answer is 1.47 times 10 to the 16th power, or 14 quadrillion 700 trillion lumens. There is nothing in the solar system so bright. And guys, the math is not wrong on this. I have run this by several people, and like I said, it's too simple. There are people here in this room that have tried to change the math and the math conditions and explain it away using mathemagics, but I'm sorry. It doesn't work. It simply doesn't work that way. So what does this prove? Well, first of all, it proves that man has never been to the moon because that's just ridiculous. And the other thing it proves is that the moon is not reflecting sunlight. Whatever is happening up there, the moon is clearly generating its own light, and it certainly is not at 14 quadrillion lumens. All right? So that's it. I'm out of time. I hope you enjoyed the presentation. Thank you very much, guys. All right, yes. Excuse me? Oh, you would be evaporated just from the light intensity. So, okay, Rick. Where is Rick? I'll give it to him. Thanks, guys.